A visitor from beyond our solar system just spoke. For the first time in human history, we've received a signal from something that doesn't belong to our solar system. Not a whisper from a distant star, not an echo from a planet billions of miles away, but a clear, undeniable radio transmission from an object that wandered into our cosmic neighborhood from the void between the stars. This object, 3I Atlas, has been silent throughout its entire journey until now. So why is it suddenly speaking? How is that even possible? Let me be clear about something right from the start. This isn't science fiction. This isn't speculation wrapped in hope. This is verified data collected by one of the most advanced radio telescope arrays on Earth, processed by astronomers who've spent their entire careers distinguishing cosmic noise from genuine phenomena. The signal is real. The source is confirmed. And yet, everything about this discovery challenges what we thought we knew about visitors from beyond our solar system. You're probably thinking what everyone thought when the news first broke. Alien probe, extraterrestrial technology. The moment humanity has been waiting for since we first looked up at the stars and wondered if we're alone. I understand that impulse. I felt it too. But here's where the story gets more fascinating than any alien narrative could ever be. Because the truth about this signal reveals something profound about the universe that we're only beginning to understand. And before I tell you what that truth is, you need to understand why this discovery is so unprecedented that it's forcing scientists to rewrite sections of their textbooks. 3I Atlas entered our solar system as a mystery. Unlike the planets, asteroids and comets that were born alongside our Sun 4.5 billion years ago, this object came from somewhere else entirely. It travelled through the darkness between stars for potentially millions of years before gravity gently pulled it into our neighbourhood. When astronomers first identified it as an interstellar visitor, the third such object ever confirmed, the scientific community held its collective breath. Because the first interstellar object we ever detected, Oumuamua, sparked years of debate and speculation that still hasn't been fully resolved. Some scientists argued it was just an unusual comet. Others suggested its acceleration patterns and shape were inconsistent with natural objects. The mystery of Oumuamua taught us that interstellar visitors don't always play by the rules we've established studying objects born in our own solar system. So when 3I Atlas appeared, astronomers watched it with intense scrutiny, deploying every tool in their arsenal to understand its nature before it slipped away forever. Multiple telescopes tracked its trajectory. Spectrometers analysed the light reflecting off its surface. Observers monitored its brightness as it tumbled through space. And throughout all of this, for months there was silence. No radio emissions, no unusual energy signatures, just reflected sunlight and the normal characteristics you'd expect from a dirty snowball of rock and ice, wandering through the void until October 2025. That's when MeerKAT, the sophisticated radio telescope array in South Africa, detected something that made astronomers stop and stare at their monitors in disbelief. A radio signal at a very specific frequency emanating from 3I Atlas. Not random noise, not interference from Earth, but a clear emission at 18 centimeters wavelength, the signature frequency of hydroxyl radicals, OH molecules that form when water breaks apart under the intense radiation of the sun. Now, here's where your mind might race ahead of the facts. A signal from an interstellar object sounds like the setup for first contact, doesn't it? But pause for a moment and consider what makes this discovery so much more intriguing than a simple alien probe narrative. This signal tells us that 3I Atlas is alive in a way we've never witnessed before in an interstellar visitor. Not alive with biology or technology, but alive with chemistry, with transformation, with processes that are revealing the composition and history of an object that formed in an entirely different stellar system than our own. The hydroxyl emission detected by MeerKAT indicates that 3I Atlas is outgassing. Water ice locked within its structure for potentially millions or even billions of years is now sublimating, transforming directly from solid to gas as the object approaches the sun's heat during its perihelion passage. And when that water breaks apart under solar radiation, it creates hydroxyl radicals that emit at a very specific radio frequency that telescopes can detect from millions of miles away. This is the signal. This is the voice of 3I Atlas. Not a message, not a beacon, but the natural radio signature of an ancient comet from another star system, revealing its chemical secrets for the first time. But why now? Why did 3I Atlas remain radio silent throughout its approach, only to suddenly emit this signal? The answer lies in understanding the relationship between comets and the Sun. As 3I Atlas travelled through the cold outer reaches of our solar system, it was essentially dormant. At those distances, solar radiation is too weak to sublimate the ices locked within the comet's nucleus. But as it swung closer to the Sun, crossing the threshold where solar heating becomes intense enough to drive chemical reactions, 3I Atlas woke up. The outgassing began. The hydroxyl radicals formed. And for the first time, this traveller from beyond our stars started broadcasting its presence to anyone listening with the right equipment. This is the moment where I need you to really absorb what's happening here. We are detecting in real time the chemical transformation of matter that originated in an entirely different solar system. The water molecules breaking apart to create this radio signal didn't form around our Sun. They crystallized around a different star, in a protoplanetary disk that gave birth to planets and comets we will never see, in a system that might be hundreds of light years from Earth. And now, that water is revealing itself to us through the universal language of physics and chemistry. The detection confirms what many astronomers suspected but couldn't prove until now. 3 Atlas is almost certainly an interstellar comet, not an asteroid. Not a piece of planetary debris, but a primordial ice and rock mixture that has preserved within its frozen heart the chemical fingerprint of its birth star system. And that fingerprint is now being transmitted to Earth in the form of hydroxyl radio emissions that tell us this object contains significant amounts of water, one of the most fundamental molecules in the universe, and a key ingredient for life as we know it. I want you to think about the odds of this moment. In all of human history, we've only confirmed 3 interstellar objects passing through our solar system, 3 visitors from the cosmic ocean that surrounds us. And now, with 3I Atlas, we're not just watching from a distance, we're listening. We're hearing its chemical voice. We're learning its secrets in ways that weren't possible with previous visitors. This is the first time we've ever detected a radio signal from an interstellar comet, and that first time is happening right now in your lifetime, during this brief window when 3I Atlas is close enough to the Sun to activate and close enough to Earth for our telescopes to capture its emissions. The scientific community is buzzing with activity. Research papers are being written. Data is being analysed from multiple observation platforms. Because this signal represents more than just a detection. It represents validation of methods that can be applied to future interstellar visitors. It proves that radio astronomy can reveal the chemical composition of objects from beyond our solar system in ways that optical observation alone cannot achieve, and it opens a new chapter in our ability to study the universe beyond our cosmic neighbourhood. But I see the question in your eyes, the skepticism, the voice in the back of your mind saying, how do we know this is really just a natural comet? How do we know there isn't something more to this signal? And that's exactly the right question to ask. That's the critical thinking that separates genuine investigation from blind acceptance. So let me take you deeper into what the data actually shows, what the science really says, and why this natural explanation is far more extraordinary than any artificial alternative could be. Because understanding the truth about this signal requires us to explore the science behind hydroxyl emissions, the nature of cometary outgassing, and the specific conditions that allow us to detect these phenomena from objects travelling through our solar system. And that journey into understanding starts with unpacking the physics and chemistry that make this signal possible in the first place. To understand what 3I Atlas is telling us, you need to understand the language it's speaking, and that language is written in the physics of molecular bonds, the behaviour of ice under radiation, and the specific radio frequencies that hydroxyl radicals emit when they form in the harsh environment of space. This isn't abstract theory. This is measurable, predictable science that we've confirmed thousands of times with comets born in our own solar system. The difference is that we're now applying this knowledge to an object that came from somewhere else entirely. Let me walk you through what happens when a comet approaches the Sun. Deep within the comet's nucleus, locked in a frozen matrix of rock and ice, are molecules of water, simple H2O. 2 hydrogen atoms bonded to 1 oxygen atom. At the frigid temperatures of the outer solar system, these molecules remain solid, trapped in crystalline structures that can persist unchanged for billions of years. The comet is dormant, a flying iceberg preserving the chemical conditions of its birth environment. But as the comet's orbit brings it closer to the Sun, everything changes. Solar radiation, particularly ultraviolet light, begins to heat the surface of the nucleus. At a certain threshold, roughly around the orbit of Jupiter, though varying based on the comet's composition, the ice begins to sublimate, not melt. Sublimate. That's a crucial distinction. In the vacuum of space, solid ice transforms directly into gas without passing through a liquid phase. Water molecules break free from the solid matrix and stream away from the nucleus, forming what we see as the comet's coma, the fuzzy envelope of gas and dust surrounding the solid core. But here's where the chemistry gets fascinating. Once those water molecules escape into space, they're exposed to intense solar radiation that wasn't strong enough to reach them. While they were buried in the nucleus, ultraviolet photons from the Sun strike the water molecules and break them apart in a process called photodissociation. The bonds holding the hydrogen and oxygen together snap, and when they do, they create hydroxyl radicals, OH molecules that are highly reactive and have a very specific property that makes them detectable across vast distances. Hydroxyl radicals emit radio waves at a precise frequency, 1665.402 MHz, which corresponds to a wavelength of about 18 centimeters. This emission happens because of quantum mechanics. The OH molecule can exist in different energy states, and when it transitions from a higher energy state to a lower one, it releases the excess energy as a photon at that specific frequency. This isn't random. This is as consistent as gravity. Every hydroxyl radical in the universe, whether it forms near Earth or in a comet from another star system, emits at the same frequency. It's a universal signature that radio astronomers can detect with extraordinary precision. This is exactly what MeerKAT detected from 3I Atlas. The radio signal at 18 centimeters isn't mysterious. It isn't unexplained. It is the direct, measurable consequence of water ice sublimating from the comet's nucleus and breaking apart under solar radiation to form hydroxyl radicals that then emit at their characteristic frequency. We've seen this signature from hundreds of comets in our own solar system. What makes the 3I Atlas detection special isn't the nature of the signal, but the source. For the first time, we're detecting this signature from water that originated beyond our Sun's influence. Now, you might wonder why we didn't detect this signal earlier if 3I Atlas has been in our solar system for months. The answer lies in understanding the relationship between solar distance and outgassing intensity. Comets don't outgas at a constant rate. The farther from the Sun, the weaker the outgassing. As 3I Atlas approached perihelion, its closest point to the Sun, which occurred in late October 2025, the heating intensified dramatically. The sublimation rate increased, more water molecules escaped, more hydroxyl radicals formed, and the radio emission became strong enough for telescopes like MeerKAT to detect it, above the background noise of space. The timing of the detection also tells us something profound about the composition of 3I Atlas. Not all comets produce strong hydroxyl emissions. The intensity depends on the amount of water ice in the nucleus, the structure of the ice matrix, and how efficiently the comet releases gas as it heats. The fact that MeerKAT detected a clear signal indicates that 3I Atlas contains substantial amounts of water ice, comparable to what we see in comets from our own Oort cloud. This similarity is itself remarkable. It suggests that the conditions that formed comets in our solar system, the temperatures and chemical processes that locked water into icy nuclei, also occurred in the distant stellar system where 3I Atlas originated. But the detection goes beyond just confirming water content. The hydroxyl emission data allows astronomers to calculate the outgassing rate, the amount of water being lost per second as the comet heats. Early estimates from the MeerKAT data suggest that 3I Atlas is releasing water at a rate consistent with a nucleus several kilometers in diameter, typical for long-period comets. This helps constrain the size and mass of the object, details that are difficult to determine from optical observations alone because the brightness of the coma can overwhelm the faint light reflected by the solid nucleus. The radio detection also provides clues about the distribution of ice within the nucleus. If 3I Atlas were just a solid ice ball, we'd expect very different outgassing patterns than what we observe. The data suggests a more heterogeneous structure, with ice mixed among rocky material, creating a porous matrix that allows gas to escape through cracks and channels as the surface heats. This structure matches theoretical models of how comets form in protoplanetary disks, where ice grains and rocky dust clump together through countless collisions over millions of years, building up layers that preserve the chemical diversity of the disk environment. What's particularly intriguing is comparing the hydroxyl emissions from 3I Atlas to those from solar system comets. Radio astronomers can measure subtle differences in the emission spectrum that reveal information about the physical conditions in the coma, such as temperature, density, and the expansion velocity of the gas. Early analysis suggests that the hydroxyl emission from 3I Atlas is remarkably similar to what we see from comets born around our Sun. The gas is expanding at comparable speeds. The emission profile matches the expected shape for a comet at that solar distance. Everything about the signal screams normal comet physics, just applied to an object with an extraordinary origin story. This is where the elegance of science really shines. We have a framework, built over decades of studying comets in our own solar system, that predicts exactly what radio emissions should look like for a comet of a given size at a given distance from the Sun. And when we point our radio telescopes at 3I Atlas, the data fits that framework beautifully. There are no anomalies in the emission spectrum, no unexpected frequencies, no modulations or patterns that would suggest anything other than natural outgassing and photodissociation. The signal is precisely what physics and chemistry predict it should be. But here's what makes this even more compelling. Radio astronomy isn't just passive observation. By detecting hydroxyl emissions, astronomers can track how the outgassing evolves over time as the comet's distance from the Sun changes. After perihelion, as 3I Atlas begins its journey back out into the cold outer solar system, the outgassing will decline, the hydroxyl emission will weaken, and eventually, as the comet crosses back beyond the threshold where solar heating is insufficient to sublimate ice, the signal will disappear. The comet will fall silent again, returning to its dormant state. That predictable pattern is already being observed, with emission intensity tracking the expected curve based on solar distance. This temporal evolution of the signal is perhaps the strongest evidence that what we're detecting is natural comet behavior rather than any artificial source. An artificial transmitter would have different characteristics. It wouldn't naturally intensify as solar distance decreased and then fade as distance increased. It wouldn't emit at the exact frequency associated with hydroxyl transitions, and it wouldn't show the spectral characteristics of expanding gas in a comet coma. The signal fits the comet model so perfectly that invoking any alternative explanation requires ignoring the simplest, most consistent interpretation of the data. Yet, I know there's still a part of your mind that wants to hold on to the possibility of something more, something unprecedented, and that's not wrong. That curiosity is what drives science forward, but satisfying that curiosity means looking at all the evidence, not just the parts that confirm what we want to believe. So let's confront the alien probe hypothesis directly. Let's examine what the data would look like if 3I Atlas were artificial, and why the hydroxyl signal we're detecting doesn't match that profile at all. Because understanding what something is requires understanding what it isn't, and that means honestly evaluating the alternatives before accepting the conclusion that best fits the evidence I need to address the elephant in the room, the headline that spread across social media faster than the actual science, the speculation that lit up comment sections and conspiracy forums the moment news broke about a signal from 3I Atlas alien probe. Extraterrestrial beacon. Proof that we're being watched. You saw those headlines. You felt that surge of excitement. And you're wondering if there's any truth behind them, if maybe, just maybe, the scientists are missing something obvious, or covering up something profound. So let me walk you through exactly why the alien hypothesis doesn't just fail to explain the data, it actively contradicts what we're observing. First, let's establish what an artificial signal would actually look like. If 3I Atlas were a probe designed by an extraterrestrial intelligence, whether active or dormant, whether intentionally transmitting or accidentally leaking radiation, the radio emissions would have very different characteristics than what we're detecting. Artificial signals, especially those designed for communication or navigation, tend to be narrowband, meaning they concentrate energy at a very specific frequency, with little spread natural emissions from hydroxyl radicals. By contrast, show a characteristic spectral profile with specific line shapes determined by the physical conditions in the gas cloud. The MeerKAT detection shows exactly that natural profile. Moreover, an artificial transmitter would show stability or modulation patterns that reflect its designed purpose. Communication signals often show timing patterns, repeating sequences, or information encoding that manifests as variations in intensity or frequency over time. Navigation beacons might show periodic pulses or sweeps across frequencies, but the hydroxyl emission from 3I Atlas shows none of these characteristics. The intensity varies smoothly with solar distance, exactly as we'd predict for outgassing, that increases near perihelion and decreases as the comet recedes. There's no modulation, no periodicity beyond what you'd expect from the comet's rotation, affecting which parts of the nucleus are illuminated. No patterns that suggest intentional encoding of information. The frequency itself is another telling clue. Why would an artificial transmitter broadcast at exactly 1665.402 MHz, the precise frequency of hydroxyl emission? That frequency isn't special for communications. It's actually within a protected band that Earth-based transmitters avoid because astronomers use it to study hydroxyl emissions from comets and interstellar clouds. If you were designing a probe to communicate with other civilizations, you might choose frequencies associated with fundamental physical constants, like the 1420 MHz hydrogen line, which has long been proposed as a universal frequency for interstellar communication. But hydroxyl at 18 centimeters, that's nature's frequency, not an engineer's choice. Some have argued that the timing of the signal's appearance is suspicious, that 3I Atlas remained silent until it got close to Earth, suggesting it might be responding to our presence or our transmissions. But this argument crumbles when you understand comet physics. The signal didn't appear when 3I Atlas got close to Earth. It appeared when 3I Atlas got close to the Sun, which is exactly when outgassing physics predicts hydroxyl emissions should become detectable. The correlation isn't with Earth's position but with solar distance. And that correlation is perfect, following the mathematical relationship between solar heating and sublimation rate that we've confirmed with countless solar system comets. Let's also address the assumption that seems to underlie much of the speculation, that an interstellar object must be artificial simply because it came from another star system. This assumption reveals a bias in how we think about interstellar space. We tend to imagine the void between stars as empty, as if objects either orbit stars or don't exist at all. But the reality is that space is filled with rogue objects, planets ejected from their birth systems, comets kicked out by gravitational interactions, asteroids freed by stellar encounters. Simulations suggest there could be trillions of interstellar objects in our galaxy alone, vastly outnumbering the stars themselves. The fact that one occasionally passes through our solar system isn't suspicious, it's statistically inevitable. And here's the crucial point that often gets lost in speculation. We've now studied 3I Atlas with multiple instruments using multiple techniques. Optical telescopes have analysed the sunlight reflecting off its surface, revealing a spectrum consistent with rocky and icy material similar to solar system comets. The colour measurements show the reddish tint typical of organic-rich surfaces exposed to cosmic radiation over long timescales. The morphology of the coma and tail match what we see in natural outgassing, with dust and gas following trajectories determined purely by solar radiation pressure and the comet's motion through space. Every measurement from every instrument points to the same conclusion: natural comet. Some researchers, and I want to be fair here, have suggested that we should keep an open mind about all possibilities until we have definitive proof, and in principle, that's good scientific practice. But keeping an open mind doesn't mean treating all hypotheses as equally likely when the evidence clearly favours one explanation over others. The burden of proof lies with those proposing extraordinary claims, and the claim that 3I Atlas is artificial is extraordinary. To justify that claim, you'd need to explain why the object looks like a comet, acts like a comet, emits signals like a comet, and matches all predictions of comet physics if it's actually a probe. That requires adding layers of assumptions that the natural explanation doesn't need. Consider the principle of parsimony, often called Occam's razor. When multiple explanations fit the observations, the one requiring the fewest unsupported assumptions is most likely correct. The natural comet explanation requires only physics and chemistry. We've already confirmed through decades of studying solar system comets. The artificial probe explanation requires assuming that extraterrestrial civilizations exist, assuming they've developed interstellar travel, assuming they've sent probes to our solar system, assuming one of those probes happens to look and act exactly like a natural comet, and assuming the hydroxyl emission we're detecting is somehow mimicry or coincidence rather than actual outgassing. Each of those assumptions is an additional unsupported layer that makes the hypothesis exponentially less likely. Now, I want to acknowledge something important. The search for extraterrestrial intelligence is legitimate science. SETI researchers have spent decades developing rigorous methods to distinguish artificial signals from natural phenomena, and those methods are being applied to interstellar objects. When Oumuamua passed through our solar system, the Breakthrough Listen project targeted it with radio telescopes specifically to search for artificial transmissions. They found nothing. No narrowband signals, no modulated transmissions, nothing that couldn't be explained by natural processes or background noise. Similar monitoring was conducted on the second interstellar object, 2I/Borisov, with the same result. And now, with 3I Atlas, the signal we're detecting is clearly natural hydroxyl emission, not an artificial transmission. The scientific consensus on 3I Atlas is remarkably strong. Researchers from multiple institutions using different telescopes and different analysis methods have all reached the same conclusion. This is an interstellar comet undergoing normal outgassing as it passes through the inner solar system. That consensus isn't the result of closed-mindedness or unwillingness to consider alternatives. It's the result of overwhelming evidence pointing in the same direction. And in science, consensus built on evidence is how we distinguish reliable knowledge from speculation. But here's what I find most fascinating about the alien probe speculation. It actually makes 3I Atlas less interesting than what it really is. An artificial probe would tell us about the civilization that built it, which would be profound, but it wouldn't tell us much about the universe itself. A natural interstellar comet tells us about the conditions in other stellar systems, about the chemical processes that form planetary systems across the galaxy, about the age and evolution of objects that travelled through interstellar space for timescales we can barely comprehend. The truth about 3I Atlas is that it's a messenger, not carrying an intentional message from alien engineers, but carrying chemical information encoded in its very structure about the distant place and time of its formation. And that brings us to the question that matters most. If 3I Atlas is a natural comet, why does it seem so unusual? Why does it spark speculation at all? Because while the hydroxyl signal confirms its cometary nature, 3I Atlas does exhibit some characteristics that are rare, that make it stand out from typical comets we've studied. Those characteristics aren't evidence of artificial origin, but they are evidence of an extraordinary journey and an origin in conditions different from our solar system. Understanding those unusual traits requires us to look closely at the specific features that make 3I Atlas unique among the objects we've observed, and that's where the story gets truly fascinating. Every comet has its quirks, its peculiarities that make it slightly different from every other comet we've observed. But 3I Atlas stands out even among a population known for diversity, and those unusual traits are what fuel speculation, what make headlines, what convince some people that there must be more to this story than scientists are telling us. So let's examine those traits directly, one by one, and understand what they actually reveal about this traveller from beyond our solar system. The first thing that caught astronomers' attention was 3I Atlas's speed. When the object was first tracked, its velocity relative to the Sun immediately flagged it as hyperbolic, meaning its trajectory wasn't bound to our solar system. It wasn't in an elliptical orbit that would eventually bring it back. It was passing through, following a path that would carry it back out into interstellar space, and even accounting for the Sun's gravity, which speeds up any object as it falls inward and slows it as it climbs back out. 3I Atlas retained an excess velocity indicating it came from outside. Estimates put its original interstellar velocity at somewhere around 14 to 17 kilometers per second, fast enough to traverse the distance from Earth to the Moon in about half an hour. But here's what you need to understand, that speed isn't evidence of propulsion or control. It's evidence of origin. Objects in interstellar space don't just sit still. They orbit the galactic center along with all the stars in the Milky Way, moving at hundreds of kilometers per second relative to distant galaxies. But relative to each other, stars and interstellar objects in the same region of the galaxy move at a range of velocities typically between 10 and 30 kilometers per second. 3I Atlas's speed fits perfectly within that range. It's exactly what you'd expect for an object drifting through interstellar space until it happened to encounter our solar system's gravitational influence. The trajectory itself is also revealing. By backtracking the path of 3I Atlas through space and accounting for its velocity, astronomers can estimate the general direction from which it came. The calculation suggested originated from somewhere in the direction of the constellation Draco, from a region that doesn't correspond to any nearby stars that we know of. This tells us that 3I Atlas has likely been travelling through interstellar space for an immense period, potentially millions of years, long enough that the star system where it formed has moved to a different position in the galaxy due to galactic rotation. The object is ancient, a relic from a stellar system that might not even exist anymore in any recognisable form. Another feature that's garnered attention is the comet's composition, particularly its unusually high carbon dioxide content. Spectroscopic observations during the months leading up to perihelion detected strong carbon dioxide emissions, indicating that the nucleus contains substantial amounts of CO2 ice, along with water ice. In our own solar system, carbon dioxide is common in comets, but the ratio observed in 3I Atlas appears somewhat higher than typical. Some have pointed to this as evidence of exotic origin or unusual formation conditions, but the reality is that we don't have a large enough sample size of interstellar comets to know what's typical and what's unusual for objects formed around other stars. The high CO2 content actually tells us something scientifically valuable. Carbon dioxide is more volatile than water, meaning it sublimates at lower temperatures and greater distances from the Sun. The fact that 3I Atlas still retains significant carbon dioxide after potentially millions of years in interstellar space suggests it has been cold enough throughout its journey to preserve these volatile ices. This preservation gives us a snapshot of the comet's original composition, less altered by heating and outgassing than comets that have made multiple passes through the inner solar system. In a sense, 3I Atlas is more pristine, more representative of the conditions in its birth environment than comets we've studied that have been modified by repeated solar encounters. Then there's the brightness behaviour, which has been erratic and difficult to predict. In the months leading up to perihelion, 3I Atlas showed unexpected surges in brightness, moments when it suddenly became more visible in telescopes before fading again. These outbursts are common in comets, and are usually associated with sudden releases of gas and dust from the nucleus, possibly from the collapse of surface structures or the exposure of fresh ice as surface layers sublimate away. But the timing and intensity of 3I Atlas's outbursts didn't follow patterns that astronomers could easily predict based on its distance from the Sun alone. This unpredictability has led to speculation about internal activity, about structural features or composition variations within the nucleus that cause uneven outgassing. And that speculation is probably correct, but there's nothing artificial about it. Comet nuclei aren't uniform. They're heterogeneous mixtures of ice, rock, and organic material that accumulated over millions of years in protoplanetary disks. Some regions might be ice-rich, others rock-rich. Some areas might have more volatile ices like carbon monoxide or nitrogen, which sublimate explosively at certain temperatures. As the comet rotates, different areas are exposed to sunlight, creating variations in outgassing that manifest as brightness changes we observe from Earth. One of the most visually striking features of 3I Atlas has been its antitail, a phenomenon where the tail appears to point toward the Sun rather than away from it. This sounds impossible at first, since comet tails form when solar radiation and solar wind push gas and dust away from the nucleus. But antitails are actually a well-understood optical illusion. They occur when Earth's position relative to the comet places us in the plane of the comet's orbit, allowing us to see the broad, flat dust trail that the comet leaves behind along its orbital path. From our perspective, this dust trail projects both ahead and behind the nucleus, creating the appearance of a tail pointing in both directions, including one that seems to point sunward 3. Atlas displayed this phenomenon beautifully during October 2025 as it passed perihelion. The images captured by amateur and professional astronomers showed both the normal gas and dust tail streaming away from the Sun and the antitail pointing back along the comet's path. Some interpreted this as evidence of active propulsion, as if the comet were a rocket ship expelling material in both directions. But the explanation is purely geometric and optical, a consequence of viewing angle rather than unusual activity. Similar antitails have been observed in dozens of solar system comets under the right geometric conditions. The size of 3I Atlas has also been a subject of discussion, though with significant uncertainty. Estimating the size of a comet nucleus is notoriously difficult, because what we see is the coma, the cloud of gas and dust surrounding the solid nucleus, which can be thousands of times larger than the nucleus itself. Based on the brightness and the estimated reflectivity of the surface, Astronomers estimate the nucleus of 3I Atlas is somewhere between 1 and 3 kilometers in diameter. That's substantial, comparable to many long-period comets from our Oort cloud, but not extraordinarily large. The uncertainty in this estimate is considerable because we don't know the exact reflectivity, or albedo, of the surface. If the surface is very dark, the nucleus could be larger than estimated. If it's more reflective, it could be smaller. What makes this size estimate particularly interesting is what it implies about the mass and longevity of 3I Atlas. A nucleus several kilometers across contains enough ice and rock to survive many perihelion passages in a solar system, or in this case, to retain substantial volatile material even after millions of years in interstellar space. The object we're observing isn't a tiny fragment, but a substantial comet that represents a significant sample of material from its parent system. Whatever chemical and isotopic signatures it carries in quantity, making it a valuable target for detailed study, despite the challenges of observing a fast-moving interstellar visitor. The rotation state of 3I Atlas adds another layer of complexity. Observations of the light curve, the way the comet's brightness varies over time, suggest it's tumbling rather than rotating smoothly around a single axis. This tumbling motion is common in comets and asteroids that have undergone collisions or gravitational encounters that transferred angular momentum in complex ways. For 3I Atlas, the tumbling could be the result of its ejection from its parent system, possibly through a close gravitational encounter with a planet or another comet that not only sent it into interstellar space but also set it spinning in an irregular way. Alternatively, the tumbling could have developed during its millions of years in space due to outgassing torques, where jets of gas erupting from the surface exert forces that alter the object's rotation over time. All of these unusual features, the high speed, the composition differences, the brightness variations, the anti-tail, the size uncertainty, the tumbling rotation, each one by itself might seem curious. Together, they paint a picture of a comet that's been through an extraordinary journey. But nothing about these features requires explanation beyond natural processes. Everything we observe is consistent with a comet that formed in another stellar system, was ejected through gravitational dynamics, travelled through the cold darkness of interstellar space for eons, and is now passing through our solar system, where we have the rare privilege of observing it up close. The anomalies aren't evidence of artificiality. They're evidence of an alien origin, alien in the sense of foreign, from somewhere else, carrying information about conditions and processes in a part of the galaxy we can never directly visit. And that realization shifts how we should think about 3I Atlas. This isn't just another comet. It's a sample return mission that we didn't have to launch, a scientific opportunity that arrived on our doorstep carrying data about another stellar system, encoded in its composition and behavior. To fully appreciate that opportunity, we need to understand the timeline of observations, the sequence of discoveries that built our current understanding, and the remarkable precision with which astronomers tracked this fleeting visitor through our cosmic neighborhood. Let me take you through the journey of discovery, the sequence of observations that transformed 3I Atlas from a faint point of light into one of the most scientifically valuable objects astronomers have studied in years. Because this isn't just a story about detecting a signal, it's a story about human persistence, about the global network of telescopes and observers that came together to track this visitor, and about the narrow window of opportunity that made any of this possible. The initial detection of 3I Atlas happened months before the radio signal discovery, when automated survey telescopes scanning the sky for near-Earth objects and potential threats flagged an unusual object with a trajectory that didn't match anything in the catalogue of known solar system objects. The preliminary orbital calculations showed a hyperbolic trajectory, immediately raising interest because such orbits indicate an object not bound to the Sun, potentially an interstellar visitor. But orbital calculations from early observations always carry uncertainty, and astronomers needed more data to confirm whether this was truly from beyond our solar system or just an unusual solar system comet on a very elongated orbit. Follow-up observations came quickly. Telescopes around the world targeted the object, measuring its position with increasing precision as it moved against the background stars. Each measurement refined the orbital calculation, reducing the uncertainty and strengthening the case that this was indeed interstellar. Within weeks, the classification was confirmed. 3I Atlas, the third interstellar object ever discovered, and only the second interstellar comet after 2, I/Borisov. The discovery sparked immediate interest because it offered a chance to study an object from another stellar system, with far more advance notice than we had with Oumuamua, which was already on its way out of the inner solar system when discovered. As 3, Atlas moved inward toward the Sun through the late summer and early autumn of 2025, observatories initiated coordinated monitoring campaigns. Optical telescopes tracked its brightness and measured its spectrum, analysing the sunlight reflecting off its surface and the light emitted by gases in its coma. These observations detected water vapour, carbon dioxide, carbon monoxide, and various other molecules typical of cometary outgassing. The spectrum showed organic compounds, likely complex carbon-based molecules that form in cold, radiation-exposed environments. Everything pointed to a comet, but the interstellar origin meant every detail was scientifically precious. By mid-October 2025, 3I Atlas was approaching perihelion, its closest point to the Sun at a distance roughly equivalent to Earth's orbit. This is when cometary activity typically peaks, when solar heating is most intense and outgassing reaches maximum rates. Astronomers knew this would be their best chance to study the object in detail before it began its journey back out into the outer solar system, and eventually beyond. Telescopes were booked months in advance. Observation schedules were carefully coordinated to maximize coverage across different wavelengths and different instruments. The MeerKAT radio telescope in South Africa, with its 64 individual dishes working together as an array, was brought into the observation campaign specifically to search for hydroxyl emissions. Previous interstellar visitors hadn't been studied with this level of radioastronomical scrutiny, partly because the telescopes weren't available, and partly because the objects weren't bright enough or active enough to produce detectable radio emissions. But with 3I Atlas showing strong outgassing in optical observations, the conditions seemed right for a radio detection if the comet contained sufficient water ice. The detection came during observations in late October 2025, coinciding almost perfectly with perihelion passage. MeerKAT detected the characteristic 18-centimetre emission of hydroxyl radicals at the expected frequency. The signal strength indicated substantial water outgassing, with estimates suggesting thousands of kilograms of water were being released per second as the Sun's heat drove sublimation across the nucleus surface. This was the breakthrough, the first confirmed radio detection of an interstellar comet, and it provided data that optical observations alone could never capture. What made the radio detection particularly valuable was its ability to measure the outgassing rate directly. Optical observations can see the coma, but translating that brightness into an actual mass loss rate requires assumptions about dust-to-gas ratios, particle sizes, and reflectivity. Radio observations of hydroxyl emission provide a much more direct measurement, because the emission intensity is proportional to the number of hydroxyl molecules, which in turn is related to the water production rate through known photodissociation physics. The MeerKAT data gave astronomers their first reliable measurement of how much material 3I Atlas was losing as it passed perihelion. Simultaneously, optical telescopes were capturing images of the comet's coma and tail. The images showed the classic structure of an active comet, a bright central condensation where the nucleus was surrounded by dense gas and dust, a broad coma extending hundreds of thousands of kilometers, and twin tails streaming behind as the comet moved through space. The gas tail, ionized by solar radiation and shaped by the solar wind's magnetic fields, appeared blue in color-filtered images. The dust tail, composed of larger particles pushed by radiation pressure, showed a yellow-white color from reflected sunlight. And the anti-tail, that optical illusion I mentioned earlier, appeared as a spike pointing back along the orbital path. In early November 2025, as 3I Atlas passed perihelion and began receding from the Sun, the outgassing started to decline. The hydroxyl emission detected by radio telescopes weakened, following the expected pattern as solar heating decreased. Optical brightness also began to fade, though not uniformly. Several outbursts occurred post-perihelion, brief surges in brightness suggesting structural changes in the nucleus or the exposure of fresh ice as surface layers eroded. These outbursts are common in comets that have undergone intense heating, as thermal stress cracks the surface and allows buried volatile ices to suddenly escape. Throughout this period, amateur astronomers played a crucial role in the observation campaign. With telescopes ranging from backyard setups to sophisticated amateur observatories, enthusiasts around the world captured images of 3I Atlas and submitted them to international databases where professional astronomers could access them. This distributed observation network provided nearly continuous coverage, compensating for gaps in professional telescope schedules and for the fact that any given observatory can only see the object when it's above the horizon and the sky is dark. The combined amateur-professional effort created a remarkably complete observational record of the comet's behaviour through its perihelion passage. By mid-November 2025, 3I Atlas was moving outward, past Earth's orbit, and heading toward the outer solar system. The hydroxyl emission was still detectable but weakening. The coma was shrinking as outgassing declined in the reduced solar heating. The window for detailed observation was closing. Telescopes began to shift focus to other targets, though monitoring continued at lower intensity to track any unexpected behaviour as the comet cooled. Looking at the complete timeline, what strikes me most is how much we learned in such a brief window. From initial detection to perihelion passage and beyond, the intensive observation period spanned only a few months. Yet in that time, astronomers gathered data across the electromagnetic spectrum from X-rays to radio waves, captured thousands of images, measured chemical compositions, tracked structural changes, and achieved the first radio detection of an interstellar comet. The coordination, the dedication, the sheer scientific effort invested in this one object reflects its extraordinary value as a messenger from beyond our solar system, and the data collection isn't over. As 3I Atlas continues its outward journey, moving farther from the Sun and gradually fading from view, telescopes will continue tracking it for as long as possible. Every additional measurement extends our knowledge. Every observation provides more context for understanding this remarkable visitor. But the peak has passed. The most active phase, the phase that produced the hydroxyl signal, and the rich data set we're now analysing, that phase is behind us. What remains is interpretation, analysis, and extracting every possible insight from the observations we managed to capture. And those insights are profound. They reach beyond just understanding one comet. They touch on fundamental questions about how planetary systems form, how material is transported between star systems, how chemistry evolves in the cold depths of space, and what we can learn about the galaxy by studying the objects that drift through it. That's what makes 3I Atlas so important, and that's why we need to carefully consider what this discovery means for our broader understanding of the universe. The implications of the 3I Atlas radio detection ripple outward far beyond this single object. We're standing at the threshold of a new era in astronomy, an era where interstellar visitors are no longer rare surprises but regular opportunities for scientific investigation, and the methods we've developed to study 3I Atlas, particularly the radio detection of hydroxyl emissions, provide a blueprint for how we'll study future visitors. Let me explain why this matters so much, why this discovery represents a turning point in our ability to understand the universe beyond our immediate cosmic neighbourhood. First, consider what 3I Atlas tells us about comet formation in other stellar systems. The fact that this object looks, acts, and emits like comets from our own Oort cloud suggests that the processes forming comets are universal, or at least very similar across different stellar environments. This shouldn't surprise us on one level. The physics of ice formation and the chemistry of protoplanetary disks should follow the same laws everywhere in the universe, but confirmation matters in science. Seeing those universal processes reflected in an actual object from another star system transforms theoretical expectation into observational fact. The hydroxyl detection specifically tells us that water ice is abundant in 3I Atlas, and by extension, likely common in comets from other stellar systems, water is one of the most fundamental molecules for life as we know it. Finding it in abundance in an interstellar comet suggests that the chemical building blocks of life, or at least the raw materials that could potentially support life, are distributed throughout the galaxy. This doesn't mean life is common, or that 3I Atlas carried living organisms. It means the universe is chemically rich and diverse, and the molecules essential for biology aren't rare or confined to a few special locations. The high carbon dioxide content offers another clue about formation conditions. In our solar system, the ratio of carbon dioxide to water ice in comets varies depending on where and when they formed. Comets that formed farther from the Sun in colder regions tend to have more carbon dioxide and other volatile ices. The relatively high CO2 content in 3I Atlas might indicate it formed in the outer regions of its parent system. or that the temperature conditions in that system's protoplanetary disk were generally colder than in ours. These are the kinds of comparative insights we can only gain by studying objects from different stellar systems. But the implications go beyond just chemistry. The very fact that we've now confirmed 3 interstellar objects passing through our solar system in recent years tells us something about the population density of interstellar material. If we're detecting a few objects per year with current survey capabilities, and considering that we can only detect objects that pass close enough and are bright enough to spot, the total number of interstellar objects in our vicinity must be enormous. Estimates suggest there could be thousands or millions of interstellar objects within our solar system at any given time, most too small or too distant to detect with current technology. This realization reframes how we think about our solar system's boundaries. The traditional picture of the solar system as a neat collection of planets orbiting the Sun, with a boundary somewhere beyond Neptune or in the Oort cloud, is incomplete. In reality, our solar system is constantly being visited by material from elsewhere, a constant influx of interstellar matter passing through, occasionally close enough for us to detect we're not isolated. We're part of a galactic ecosystem where material circulates between star systems, carried by the gentle gravitational currents of the galaxy. The radio detection method validated with 3i Atlas opens new possibilities for detecting and characterizing future interstellar comets. Radio telescopes can observe objects in conditions where optical telescopes struggle, such as during daylight or when the object is close to the Sun. From our perspective, radio observations also provide data about composition and activity that optical observations can't easily capture. As radio telescope technology continues to improve, with arrays like MeerKAT and the upcoming Square Kilometre Array coming online with unprecedented sensitivity, we'll be able to detect hydroxyl emissions from fainter, more distant objects, expanding our ability to study interstellar visitors. There's also an exciting possibility that 3i Atlas represents a type of object we'll see more of as our detection capabilities improve. Long-period comets from our own Oort cloud, objects with orbital periods of thousands or millions of years, are thought to be pristine samples of material from the early solar system, largely unchanged since they formed. But they've still spent their entire existence within the Sun's gravitational influence, subject to occasional perturbations from passing stars or giant molecular clouds that alter their orbits. Interstellar comets like 3i Atlas have potentially spent millions of years in true interstellar space, isolated from any star's influence, preserved at temperatures near absolute zero, making them even more pristine samples of protoplanetary disk material. The age of 3i Atlas is particularly intriguing. We can't measure its age directly, but we can infer constraints. If the comet has been travelling through interstellar space for millions of years at its observed velocity, it has covered distances of tens or hundreds of light years. The stellar system where it formed might have been much closer to our solar system when the comet was ejected, and galactic rotation has since carried that system to a different region of the galaxy. Alternatively, the comet might have been ejected from a system that's now far away, and its long journey brought it by chance into our neighbourhood. Either way, we're observing an object that's potentially older than some of the surface features on Earth, a piece of cosmic history frozen in time. The implications extend to our understanding of how material and information spread through the galaxy. If interstellar comets are common, and if they occasionally get captured into orbit around stars rather than just passing through, they represent a mechanism for transferring material between stellar systems. A comet ejected from one system, carrying ice and organic molecules formed in that system's protoplanetary disk, could be captured by another system millions of years later, delivering those molecules to a completely different environment. This process, called lithopanspermia at its most extreme, has been proposed as a potential mechanism for spreading life or its precursors between star systems. I'm not suggesting 3i Atlas is carrying life. The chances of any biological material surviving the cold, radiation, and vacuum of interstellar space for millions of years are essentially zero. But complex organic molecules, the chemical building blocks that life uses, could potentially survive. And if comets like 3i Atlas are regularly travelling between star systems, they're mixing and distributing those organic molecules across the galaxy, potentially influencing the chemistry of planetary systems they visit or get captured by. The galaxy becomes not just a collection of isolated stellar systems, but a connected chemical network where material circulates over vast timescales. The discovery also highlights gaps in our current knowledge and capabilities. We detected 3I Atlas relatively close to perihelion, which gave us a good observing window, but meant we missed the chance to study it during its approach through the outer solar system when it was cold and inactive. Future detection systems, particularly the Vera Rubin Observatory's Legacy Survey of Space and Time, which will begin operations in the coming years, are expected to detect interstellar objects much earlier, giving us months or years of advance notice. That advance warning would allow us to plan dedicated observation campaigns, possibly even spacecraft missions to intercept and study these visitors up close. Imagine what we could learn from a spacecraft mission to an interstellar comet. We could sample the ice directly, measuring isotopic ratios that reveal details about the temperature and chemistry of the protoplanetary disk where it formed. We could analyze organic molecules with laboratory instruments far more sensitive than telescopes can provide. We could see the nuclear structure, understand its composition layer by layer, and directly test theories about how comets form and evolve. Several mission concepts have been proposed for intercepting interstellar visitors, though none have been funded yet. But 3I Atlas and objects like it make the scientific case for such missions increasingly compelling. The radio detection also demonstrates that we don't need to wait for dedicated space missions to learn from interstellar visitors. Ground-based observatories, with increasingly sophisticated instruments and coordinated observation strategies, can extract enormous amounts of information from these fleeting encounters. The key is preparation, having observation plans ready, having telescope time allocated, and having the international coordination to maximize coverage. The success with 3I Atlas shows that this approach works, that we can mobilize the global astronomical community to focus on these rare opportunities and generate high-quality scientific returns. Yet, even as we celebrate what we've learned, I'm acutely aware of how much remains unknown. Every answer raises new questions, every measurement reveals gaps in our understanding, and that's what makes this field so exciting, so dynamic, so full of potential for future discovery. The study of interstellar objects is still in its infancy, with only 3 confirmed examples and limited data on each. But the trajectory is clear. As our detection capabilities improve, as our instruments become more sensitive, as our understanding deepens, we'll detect more of these visitors, study them in greater detail, and build a comprehensive picture of the interstellar population. 3I Atlas is a milestone on that journey, not the destination, and the questions it leaves unanswered are perhaps more valuable than the questions it resolved. Let's talk about what we don't know, because for all the data we've collected, for all the insights we've gained, 3I Atlas remains in many ways a mystery wrapped in ice and rock, a traveller from an unknown origin carrying secrets we've only begun to uncover. And acknowledging these gaps in our knowledge isn't a weakness, it's how science progresses. It's how we identify where to focus future efforts and what questions matter most. So let me walk you through the mysteries that keep astronomers awake at night, the puzzles that 3I Atlas presents even after months of intensive study. The most fundamental unanswered question is, where exactly did 3I Atlas come from? We can backtrack its trajectory and determine the general direction, somewhere in the direction of Draco, but that doesn't identify a specific parent star. The challenge is that the comet has likely been travelling for so long that the star system where it formed has moved significantly due to galactic rotation and its own proper motion through space, even if we knew the exact direction the comet came from when it entered our solar system. Tracing that line back millions of years requires accounting for the complex gravitational dynamics of the galaxy, the perturbations from passing stars, and uncertainties in the comet's trajectory before it encountered our Sun. The parent star could be anywhere within a volume of space hundreds of light-years across. Some researchers are attempting to narrow down candidates by looking at the comet's composition and comparing it to theoretical models of stellar systems with different properties. For example, if we could measure the deuterium to hydrogen ratio in the water ice, that would tell us about the temperature conditions when the ice formed, which correlates with distance from the star. If we could measure other isotopic ratios like oxygen 18 to oxygen 16, or carbon 13 to carbon 12, we could constrain the chemical evolution of the protoplanetary disk. But these measurements require spectroscopic precision that's challenging to achieve with a fast-moving distant object, especially now that 3I Atlas is receding and fading. Another mystery is how 3I Atlas was ejected from its parent system in the first place. Gravitational interactions with giant planets can kick comets into the outer reaches of a stellar system, or even eject them into interstellar space entirely. This is probably how most interstellar comets form. But the specific dynamics matter because they determine the velocity and direction of ejection, which in turn affects where the comet ends up millions of years later. Was 3I Atlas ejected during the formation phase of its stellar system, when planets were still migrating and gravitational interactions were chaotic? Or was it ejected later by a close encounter with a rogue planet or during a stellar flyby? We don't know, and without knowing where it came from, we can't reconstruct its history. The internal structure of 3I Atlas remains largely unknown. We've observed the surface and the coma, but what lies beneath? Is the nucleus homogeneous, a uniform mixture of ice and rock throughout? Or is it layered, with different compositions at different depths, reflecting the changing conditions during formation? Does it have large voids, pockets of weakness that could cause it to fragment if heated too intensely? The outbursts we observed suggest structural heterogeneity, but we can't image the interior with current technology. Understanding internal structure matters because it affects how the comet responds to solar heating, how it outgasses, and ultimately how long it can survive as a coherent object. The rotation state and its evolution add another layer of mystery. We know 3I Atlas is tumbling, but the precise rotation period and axis orientation are uncertain. Moreover, outgassing creates torques that can alter a comet's rotation over time, potentially causing it to spin faster, slower, or change its axis orientation. For 3I Atlas, these outgassing torques are particularly interesting because they're isometric, varying as different parts of the nucleus are heated. Over the months of its perihelion passage, did the rotation state change? If we could measure that change, it would tell us about the distribution of active areas on the surface, the efficiency of outgassing from different regions, and the nucleus's response to thermal stress. There's also the question of how pristine 3I Atlas really is. I've mentioned that interstellar objects are potentially more pristine than solar system comets because they've been isolated in cold space for so long, but pristine doesn't mean unchanged. Interstellar space isn't empty. It contains gas, dust, and high-energy cosmic rays. Over millions of years, even a small flux of these particles can alter surface chemistry, breaking down complex molecules, sputtering away material, or creating new compounds through radiation chemistry. How much has the surface of 3I Atlas been processed during its interstellar journey? Does the surface composition still reflect its formation environment, or has it been modified into something new? The hydroxyl detection answered questions but raised others. The emission intensity gives us the water production rate, but it doesn't tell us about the distribution of water ice within the nucleus. Is the ice concentrated in certain regions? Is it mixed uniformly with dust and rock? The fact that we detected hydroxyl at all confirms substantial water content, but the detailed spatial distribution of that water affects how we interpret the observations and what we infer about formation conditions. Future radio observations with higher angular resolution might be able to map the hydroxyl emission across the coma, revealing which parts of the nucleus are most active. But for 3I Atlas, we don't have that level of detail. Another intriguing question is whether 3I Atlas has visited other stellar systems before ours. An object travelling through interstellar space for millions of years at 15 kilometers per second could cover significant distances, potentially passing near other stars along its journey. If it did those encounters alter its trajectory or cause heating episodes that modified its surface? Some simulations suggest that close stellar passages could temporarily activate outgassing even in interstellar space. If the star is luminous enough and the approach close enough, any such event would be brief, but it could leave signatures in the surface structure or composition that we might detect if we knew what to look for. The fate of 3I Atlas is also uncertain in some ways. We know it's on a hyperbolic trajectory that will carry it back out of the solar system, but where will it go next? Its velocity and direction after exiting our system will determine which region of the galaxy it travels through next, whether it might encounter another star system in the foreseeable cosmic future, and ultimately where it will be when our sun runs out of fuel billions of years from now. Backtracking the trajectory is hard. Projecting forward is even harder because we can't predict the gravitational perturbations it will experience from unseen rogue planets, brown dwarfs, or stellar encounters along its path. I'm also fascinated by what we didn't detect. Throughout the observation campaign, astronomers were alert for any unusual emissions, any unexpected signals that might indicate composition or activity we haven't seen before. But everything detected fell within the range of what we've observed from solar system comets. Does that mean interstellar comets are indistinguishable from our own? Or does it mean our instruments aren't sensitive enough to detect subtle differences? We can only measure what our technology allows, and there might be chemical or physical properties of 3I Atlas that remain hidden, simply because we don't have the right tools to see them yet. The comparative study of interstellar objects is still limited by small sample size. We've confirmed only 3, Oumuamua, 2e Borisov, and now 3I Atlas. That's not enough to draw broad conclusions about the diversity of interstellar populations. Are these 3 representative of typical interstellar objects, or are they outliers that happen to be detectable? We won't know until we've studied dozens or hundreds of interstellar visitors, and that will take years or decades of continued surveys and observations. Every new detection will either confirm patterns or reveal new diversity, gradually building our understanding of what's typical and what's unusual. There's also a meta-question about observation strategy. Did we study 3I Atlas optimally, or in hindsight, would different choices have yielded more valuable data? Should more telescope time have been allocated to radio observations versus optical? Should we have prioritized spectroscopy over imaging? These aren't criticisms. They're honest reflections on how we allocate limited resources when studying rare, fleeting opportunities. Every interstellar object detection is a learning experience that informs how we approach the next one, gradually refining our methods and priorities. And finally, there's the biggest question of all: what will the next interstellar visitor reveal? Will it be similar to 3I Atlas, reinforcing patterns and confirming theories? Or will it be radically different, forcing us to reconsider our assumptions about what interstellar objects can be? The universe has a habit of surprising us, of presenting phenomena we didn't predict or anticipate. Staying open to those surprises while maintaining scientific rigor is the challenge we face with every new discovery. These unanswered questions aren't frustrations, they're invitations. They're doorways to future research, to new observations, to deeper understanding. And they remind us that science is a process, not a destination. We don't study interstellar objects to close the book on cosmic mysteries. We study them to open new chapters, to ask better questions, to push the boundaries of what we know into the vast territory of what we have yet to discover. And in that context, 3I Atlas isn't an endpoint, it's a beginning, a glimpse of the richness that awaits us as we continue exploring the objects that wander through our solar system, carrying messages from distant corners of the galaxy. To truly appreciate 3I Atlas, we need to zoom out and see it as part of a larger story. A story about humanity's growing awareness that our solar system isn't a closed, isolated system, but a waypoint in a galaxy filled with wandering objects. Let me take you through the brief but profound history of interstellar object detection and place. 3I Atlas in the context of what came before and what might come after. Because this isn't just about one comet. This is about recognizing that the universe is far more dynamic and interconnected than we once imagined. The story begins with Oumuamua, the first confirmed interstellar object, detected in October 2017 by the Pan-STARRS telescope in Hawaii. The name means scout, or messenger, in Hawaiian, and it lived up to that name by completely upending our assumptions about what interstellar visitors would look like. Oumuamua's trajectory was clearly hyperbolic, proving beyond doubt that it came from outside our solar system. But everything else about it was puzzling. Its shape appeared extremely elongated, like a cigar or perhaps a pancake, based on how its brightness varied as it rotated. Its surface was unusually reflective, and most mysteriously, its trajectory showed a slight acceleration that couldn't be explained by solar gravity alone. That acceleration sparked intense debate. Some astronomers proposed that Oumuamua was experiencing outgassing, releasing jets of material that created a tiny rocket effect, similar to how comets accelerate, but no coma or tail was detected, no clear evidence of outgassing that typically accompanies such acceleration. Others suggested more exotic explanations: a light sail pushed by solar radiation pressure, a fragment of a Dyson sphere, even an extraterrestrial probe. Most scientists favoured natural explanations, proposing that Oumuamua might be composed of unusual materials like solid hydrogen, or nitrogen ice that would outgas without producing a visible coma. But the lack of definitive data left room for speculation. What Oumuamua taught us, more than anything, was that we weren't prepared. The object was detected only after it had passed perihelion and was already heading back out of the solar system. We had only a few weeks to observe it before it faded beyond detection, and in that brief window we couldn't gather enough data to resolve all the mysteries it presented. The experience was humbling but educational. It motivated efforts to improve our detection capabilities and develop faster response protocols for studying interstellar visitors before they slip away. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar object, subsequently designated 2I/Borisov. Unlike Oumuamua, there was no ambiguity about what 2I/Borisov was. It showed clear cometary activity from the moment of discovery. With a visible coma and tail, its spectrum revealed water vapor, carbon monoxide, and other molecules typical of solar system comets. It behaved exactly like a comet should, following predictable patterns of brightness increase as it approached the Sun and decrease as it receded. In many ways, 2I/Borisov was reassuring because it fit our expectations, confirming that at least some interstellar objects are straightforward, unremarkable comets that happen to have wandered in from elsewhere. The detection of 2I/Borisov several months before its perihelion gave astronomers a precious advantage: time. They could plan observation campaigns, coordinate between different telescopes and instruments, and track the comet's evolution through its entire passage. The data collected from 2I/Borisov was far more comprehensive than what we managed with Oumuamua, and it provided the first detailed chemical analysis of an interstellar comet. Surprisingly, the composition of 2I/Borisov was similar to many solar system comets, suggesting that comet formation processes might be relatively universal across different stellar systems. But 2I/Borisov also showed some distinctive features. Its carbon monoxide to water ratio was higher than typical solar system comets, and its structure seemed unusually compact and dense. These differences hinted at formation in a colder environment, or around a different type of star. The observations demonstrated that even though interstellar comets might look similar to our own at first glance, detailed study reveals subtle variations that encode information about their diverse origins. Now, with 3I Atlas, we have a third data point, and the pattern is becoming clearer. Interstellar objects aren't all exotic mysteries like Oumuamua. Some, perhaps most, are comets showing normal cometary behavior, distinguishable from solar system objects only by their hyperbolic trajectories and possibly subtle compositional differences. The hydroxyl detection from 3I Atlas reinforces this pattern. It's a comet, it outgasses, it follows known physics, but it carries information about another stellar system, making it scientifically invaluable despite its mundane behavior. Comparing the three objects is instructive. Oumuamua remains an enigma, its unusual acceleration and lack of clear outgassing still not fully explained despite numerous proposed theories. 2I/Borisov was unambiguously a normal comet, active and well-behaved. 3I Atlas falls somewhere in between, showing normal cometary activity but with unusual characteristics like high carbon dioxide content and erratic brightness variations that make it interesting even though it's clearly natural. This diversity, even from just 3 examples, suggests that the interstellar population is varied, including objects that formed under different conditions, evolved along different paths, and present different observational challenges. Beyond these confirmed interstellar objects, there have been tantalizing hints and false alarms. Various objects detected by survey telescopes initially showed orbital parameters suggesting possible interstellar origin, only to be reclassified as solar system objects after more data refined their trajectories. The challenge is that determining whether an orbit is truly hyperbolic requires very precise measurements, especially for objects that come from the outer solar system and have velocities close to the threshold between bound and unbound orbits. As our detection capabilities improve, we'll likely see more candidate interstellar objects that turn out to be borderline cases or require extensive observation to confirm their nature. There's also the question of how many interstellar objects we're missing. Current detection systems are biased toward objects that are relatively large, bright, and pass close to Earth. Smaller objects, darker objects, or those that stay farther out in the solar system could easily escape detection entirely. Statistical models based on the objects we have detected suggest there might be several interstellar visitors per year passing through the inner solar system, and potentially thousands if you count the entire volume out to Neptune's orbit. Most go unnoticed, invisible messengers carrying information we never receive, simply because we're not looking in the right direction at the right time. The comparison with signals is worth exploring too. When we talk about receiving a signal from 3i Atlas, we're using language that echoes SETI, the search for extraterrestrial intelligence, which has been scanning the skies for artificial radio transmissions from alien civilizations for decades. SETI has detected numerous candidate signals over the years. Brief, strong radio emissions that stood out from background noise and raised hopes of first contact, but every one has either failed to repeat when telescopes were pointed back at the source, or was eventually traced to terrestrial interference or natural astrophysical phenomena. The hydroxyl signal from 3i Atlas is different. It's not a candidate waiting for confirmation. It's a verified natural emission with a well-understood physical origin. But the emotional arc is similar. The excitement of detection, the speculation about meaning, and ultimately the satisfaction of understanding what SETI teaches us is the importance of rigor, of not jumping to conclusions, of carefully evaluating all explanations before accepting extraordinary claims. And that same rigor applies to studying interstellar objects. Yes, they're from beyond our solar system, which is inherently exciting, but excitement doesn't justify abandoning careful analysis or embracing unsupported theories. The field of interstellar object studies is also benefiting from advances in related areas of astronomy. The study of exoplanets, planets orbiting other stars, has exploded over the past 2 decades, with thousands of confirmed detections and increasingly sophisticated methods for characterizing their properties. Some of those same methods, particularly spectroscopy and photometry, apply to studying interstellar objects. And the discoveries about exoplanet systems, revealing incredible diversity in planet types, orbital configurations and system architectures, inform our expectations about the interstellar objects that might be ejected from those systems. Similarly, the study of protoplanetary disks, the rotating clouds of gas and dust around young stars where planets form, has advanced dramatically with telescopes like ALMA that can image these disks in unprecedented detail. We can now see the structure within disks, the gaps and rings carved by forming planets, the distribution of different molecules at different temperatures and distances from the star. This knowledge provides context for interpreting the composition of interstellar objects. When we detect high carbon dioxide in 3i Atlas, we can compare that to observations of CO2 in protoplanetary disks, an infer wherein a disk such a comet might have formed. The next frontier in interstellar object studies is likely to involve direct spacecraft missions. Several mission concepts have been proposed over the years, including small probes that could intercept an interstellar object and conduct close-up observations or even land on its surface. The technological challenges are substantial because interstellar objects move fast and often aren't detected until they're already close to perihelion, leaving little time to launch an intercept mission. But these challenges aren't insurmountable, especially if we develop spacecraft that can be launched quickly, or if future detection systems give us years of advance warning. Imagine what a spacecraft could discover. It could image the nucleus at high resolution, seeing details that ground-based telescopes can't resolve. It could sample the coma directly, analysing the gas and dust with laboratory instruments far more sensitive than remote observations allow. It could measure isotopic ratios precisely, revealing the temperature and chemical conditions when the comet formed. It could even potentially return samples to Earth, bringing material from another stellar system into our laboratories, where scientists could study it with every tool available. The scientific return from such a mission would be extraordinary, potentially revolutionizing our understanding of planetary system formation across the galaxy. But even without spacecraft missions, the future of interstellar object studies is bright. Next-generation survey telescopes like the Vera Rubin Observatory will detect interstellar objects earlier and more frequently, providing larger samples and better statistics. Improved radio telescopes will allow more sensitive detections of molecular emissions, revealing composition details we can't currently access. And as our theoretical understanding deepens, we'll be better able to interpret the observations, extracting maximum information from every data point. The story of interstellar objects is still being written, and we're living through the opening chapters. Every new detection adds another piece to the puzzle, another clue about the nature of the galaxy we inhabit. 3i Atlas is one chapter in that story, a particularly valuable one because of the hydroxyl detection and the comprehensive observation campaign, but it's not the last chapter. The universe has more messengers to send our way, more objects carrying information from distant stellar systems, and we're finally developing the tools and knowledge to read the messages they bring. That realization points forward, toward a future where studying interstellar visitors becomes routine, where every few months brings a new object to observe and analyze, and where we gradually build a comprehensive picture of the material landscape of our galaxy. So where do we go from here? You've followed the journey of 3i Atlas from its mysterious signal detection through the scientific explanations and broader implications. You understand what this object is, what it tells us, and what mysteries remain unsolved. But the story doesn't end with understanding. It ends with anticipation, with looking forward to what comes next, with recognizing that 3i Atlas is just one chapter in a much larger narrative that's still unfolding. And you're part of that narrative whether you realize it or not. Let me explain why. As 3. Atlas recedes from our solar system, growing fainter with each passing week. Astronomers are already preparing for the next interstellar visitor, because there will be a next one. The question isn't if, but when and what form it will take. Based on the 3 confirmed detections in just a few years, we can expect interstellar objects to be discovered relatively regularly, now that survey telescopes are specifically watching for them. Some will be detected early enough for comprehensive study, others might slip through barely noticed. But each one offers an opportunity to expand our understanding, to test theories, to discover something unexpected. The Vera Rubin Observatory, scheduled to begin its legacy survey of space and time in the near future, will be a game-changer for interstellar object detection. With its large mirror, wide field of view, and rapid survey cadence, it will scan the entire visible sky every few nights, detecting faint objects and tracking their motion with unprecedented efficiency. Computer algorithms will automatically flag objects with unusual trajectories, including potential interstellar visitors, allowing astronomers to begin follow-up observations within hours or days of initial detection. The early warning that Rubin provides could give us months or even years to study interstellar objects before they reach perihelion and begin their exit from our solar system. Radio telescope arrays are also improving. The Square Kilometre Array, currently under construction across sites in South Africa and Australia, will be the most sensitive radio telescope ever built when completed. Its ability to detect faint emissions, including hydroxyl and other molecular lines, will allow astronomers to study outgassing from interstellar comets in far greater detail than was possible with 3i Atlas. We'll be able to map the distribution of gas in the coma, track how outgassing varies with rotation and solar distance, and possibly detect molecules that are currently below detection thresholds. Every improvement in instrumentation opens new observational windows. But technology alone isn't enough. We also need coordination, communication, and community. The success in studying 3i Atlas came from collaboration between professional observatories, amateur astronomers, and research institutions around the world. That model will become even more important as the number of interstellar objects increases. Developing rapid response networks, sharing data in real time, and coordinating observation schedules across different time zones and instruments will maximize what we can learn from each fleeting visitor. And the amateur astronomy community plays a vital role in this network, providing continuous monitoring and backup observations that fill gaps in professional telescope schedules. There's also a need for public engagement and education. Interstellar objects capture imagination in ways that many astronomical phenomena don't. They're tangible, comprehensible, and profoundly mysterious all at once. A comet from another star system is something anyone can understand and wonder about. And that wonder can translate into support for scientific research, for funding telescopes and missions, for encouraging young people to pursue careers in astronomy and planetary science. Every time an interstellar object makes headlines, it's an opportunity to communicate science, to explain the process of discovery, to show how curiosity and rigorous investigation lead to knowledge. What I want you to take away from the 3i Atlas story isn't just the facts about hydroxyl emissions and cometary outgassing. I want you to understand the mindset, the approach that separates genuine investigation from speculation, It's about following the evidence wherever it leads, even if the destination is less sensational than alien probes. It's about asking good questions and being willing to accept answers that create new questions. It's about recognizing that nature is often more subtle, more complex, and ultimately more interesting than the simple narratives we might prefer. The universe doesn't owe us mysteries that fit our expectations. It doesn't promise alien civilizations or impossible physics or easy answers. What it offers is reality, which is simultaneously more mundane and more profound than fiction, a comet made of ice and rock, travelling between stars for millions of years, preserving within its frozen heart the chemical signature of a stellar system that might no longer exist in any recognizable form, arriving in our neighborhood purely by chance, just as we've developed the technology to detect it and understand what it is. That's not science fiction, that's science fact, and it's extraordinary. Looking forward, some of the most exciting possibilities involve detecting interstellar objects even earlier in their approach. If we could spot an interstellar comet when it's still beyond Jupiter's orbit, years before perihelion, we'd have time to plan dedicated spacecraft missions. Engineers have proposed concepts for fast response probes that could be launched on short notice, use gravitational assists to match velocity with the target, and conduct close-up studies that ground-based telescopes can't achieve. Such missions would be challenging and expensive, but the scientific payoff would be enormous. And the technological capabilities required, rapid launch systems and advanced propulsion, have applications beyond just studying interstellar visitors. There's also the tantalizing possibility of detecting active outgassing from an interstellar object, while it's still far from the Sun, potentially revealing composition details before the comet is heated and altered by solar radiation. This would require extremely sensitive telescopes and probably some luck in catching the object at just the right moment, but it's not impossible. If we could detect hydroxyl or other molecular emissions from an interstellar comet while it's still in the outer solar system, we'd be observing truly pristine material, unchanged by any recent heating, providing the most direct look possible at the comet's original composition. Another avenue for future research involves statistical studies of the interstellar object population. As we detect more examples, patterns will emerge. We'll be able to estimate what fraction are rocky asteroids versus icy comets, what the typical size distribution looks like, whether certain compositions are common or rare, and how these properties might correlate with the regions of the galaxy from which the objects originated. Building this statistical picture requires many detections, which means years of patient observation and data collection. But eventually, we'll have enough data to draw robust conclusions about the interstellar population as a whole, not just individual objects. I'm also fascinated by the potential for detecting very small interstellar objects, particles or pebbles, rather than kilometre-sized comets or asteroids. These tiny travellers are probably far more numerous than large objects, but much harder to detect because they're so faint. However, when they enter Earth's atmosphere, they create meteors, and some meteor detection networks are now sophisticated enough to calculate trajectories that might reveal interstellar origin. If we could confirm interstellar meteors and recover fragments as meteorites, we'd have actual physical samples from other stellar systems to study in laboratories. The hunt for interstellar meteorites is an emerging subfield that could yield incredible results in coming years. Ultimately, what's next depends partly on nature and partly on us. Nature will determine what objects pass through our solar system and when. We determine whether we're looking, whether we have the tools to detect and study them, and whether we're asking the right questions. The story of 3i Atlas shows that we're getting better at all of these things. We detected an interstellar comet, mobilized a global observation campaign, collected comprehensive data across multiple wavelengths, and achieved the first radio detection of hydroxyl emissions from such an object. That's progress, that's success, and it's foundation for doing even better next time. But I'll leave you with this thought. Every one of us looking up at the night sky is seeing light from objects billions of miles away, photons that travelled through space for minutes or hours or years before reaching our eyes. We're already connected to the cosmos in the most direct way possible, and when we learn about objects like 3i Atlas, when we understand their origins and their journeys, we're deepening that connection. We're not just observing the universe, we're part of it, participants in a cosmic story billions of years old, adding our own chapter through curiosity and discovery. 3i Atlas is fading now, moving back into the darkness between stars, its brief moment of visibility coming to an end. but the knowledge it gave us remains. The methods we developed to study it will be applied to future visitors. The questions it raised will drive research for years to come. And somewhere out there, the next messenger is already on its way, travelling through space at kilometres per second, carrying its own secrets and surprises. We just need to be ready when it arrives. And based on what we've learned from 3i Atlas, I'm confident we will be. The signal from 3i Atlas wasn't a message from alien engineers. It was something better, a transmission from the universe itself, speaking in the language of chemistry and physics, telling us we're surrounded by wonders waiting to be understood. And that's the real story, the enduring message that matters more than any speculation about probes or beacons. We're living in an age where the universe is revealing itself to us in ways previous generations could only imagine. The question isn't whether there are more mysteries to discover. The question is whether we're paying attention, whether we're willing to look with both curiosity and rigour, and whether we're ready for whatever truths the next cosmic visitor brings. Stay curious, stay sceptical, and keep watching the skies, because the universe has more to say, and every signal, every detection, every unexpected discovery is an invitation to understand a little more about the vast, ancient, and endlessly fascinating cosmos we call home.